computer. Great. So welcome back. We are in our second to last week, and we are doing the fundamental theorems of calculus, which is like the coolest part of this class. Okay, I don't want to lose my whiteboard. So we are going to keep on with Stokes theorem today. So today we will continue discussing Stokes theorem. And WebWork doesn't really seem to have, I can't find any good list of questions about these last theorems. So the homework is going to be mostly at the end of the, you have this homework that's due today, and there will be more homework assigned. It will not be WebWork, I don't believe, because there are lots of good written problems for this. Okay, so I'll tell you what the statement is again, because we're going to be discussing it. So let me remind you what it says. This is the statement. So you'll say, let S be an oriented surface with boundary, well, I guess I'll say with unit normal n. Okay, the boundary just means the edge of S is C, and C is oriented, and this orientation agrees with orientation of the surface. So we are going to talk more about that in a second, so I will highlight this. So agrees with orientation of S. We're going to go into that a little bit more today. And then we're going to say, let V be a vector field defined near S. So sometimes we know our vector fields can have these singularities. We want to make sure our surface is staying away from these singular locations. Okay, so in this case that Stokes theorem says, we have an equality, a double integral, which is a flux integral of the curl of V. We're going to dot that with the normal. Okay, so we talked about how to interpret this quantity yesterday, or what was it, Wednesday. So this is an integral over the surface. We're going to say this thing, Stokes theorem says that this is equal to the work done on the outside, V dot T ds. So this is just a reminder of everything that of all the lead up to this on Wednesday. Okay, so we can sort of interpret why this is true by understanding, instead of thinking of the left-hand side as the amount of curl flowing through the surface, you should really think about this as how much of V's rotation lands on S. That's a better way to geometrically think about the thing on the left. And then the thing on the right is the work done on the edge. Okay, and I also want to say something else, is that sometimes you'll see the following notation. Sometimes when we want to talk about the boundary of S, people will write this as this little, it looks like a partial symbol, like partial S. So this is not a derivative. It is, it's telling you it's the object, it's a shape. So we would say that the boundary of S is equal to C. That's how you read this. The boundary of S is C. Okay, and there's some, maybe I'll draw a quick little picture. Okay, so I've got some surface in 3D space. Okay, that's S. It has some unit normal n, and the boundary is some curve C. So that might be C. Okay, that's the picture we have in mind. So I want to talk, some people had some questions at the end of class on Wednesday about what this, like, how can you tell if an orientation of C agrees with the orientation of S? So I did mention it in class, but I want to discuss it and discuss how to determine if these things are two things agree. So I'm going to move on to this next page. None of this is material that you haven't seen before. So let's remind ourselves how to determine if the orientation of C agrees with the orientation of S. Okay, so I'll say what I said in class on Wednesday, and this is the OpenStax version. This is how they describe it in OpenStax. And it's kind of cumbersome, and I'll tell you how a different way to do it, which is kind of the way that I think is a little more intuitive. So, but I'll tell you what OpenStax says in case you like using the textbook. It says the orientation of C agrees with the orientation of S if, okay, when walking upright along C as determined by unit normal, then your left hand should hover over the surface S, not your right hand. So let me draw a picture. Okay, so I'll draw a picture of an agreeing situation and sort of a non-agreeing situation. So I've got two surfaces. Well, really, here's S, here's my normal vector N, and I'll have a curve. So here's the edge, sort of the boundary, and I'll have this direction of orientation for C on the left, but I'll flip it on the right. Okay. So here's C, and then just give you some more detail, kind of the surface. You know, you're kind of looking at the underside of some wiggly shape. Okay, so let me draw this I'm going to draw a little stick person over here on the left. On the left, as you're a stick person and you're walking along this curve here, okay, and you're upright as according to the N vector, your left arm, I'll draw it, is a really big left arm with your hands, is hovering over the S, and your right arm is not. Okay, so over here on the left, we have this is orientations agree. Okay, then you can see what'll happen on the other picture. On the other picture, your left hand will be hovering over the not S, and your right hand will be hovering over S. So here orientations do not agree. Okay, so that's one way you can think of these two things. Now let me I'm going to minimize this and tell you the way that I think about it. And I think there's a second way to do this, and I think it's a little more intuitive. Alternatively, you can do the following. So how did I write this? I say to determine if orientations agree, draw a normal vector n near boundary of C and draw small counterclockwise arrows at the base of the n. Then check if these arrows move with C or move against C. So I'll draw the very same two pictures, and I'll kind of show you what I'm talking about here. So if I've got this kind of surface, same surface, so here's S, and I've got the same N, And here's my boundary. We know the left-hand picture is the one that orientations agree, and the right-hand picture is the one for which orientations do not agree, based on the what we just did from the OpenStax way of determining these things. But my way is I'll draw a little normal vector down by the green, and I'll do this sort of counterclockwise spinning. And I know I'm seeing right here that sort of the arrows, if you were to place cogs, mechanical gears, one on the edge and one at the base of the normal vector, they'd be gliding, they'd be moving along with each other. So here we have orientations agree. And over here, if I drew, some counterclockwise rotation about a normal vector at the base, then I'd be fighting it. The cogs would be fighting the orientation over there. So do not agree. So you can use whichever way you like most. I like the second way. So let me stop talking so much and okay, we've got somebody asking a question. Okay, sorry. Okay. It's hard to tell which is the front and which is the back. Yeah, that's true. Okay, so the front of the surface on both of these pictures, this is the front up here. And think about, this is the darker underside. You're kind of like looking down and in. There's down and in for both of these pictures. Yeah, that's down and in, and this is sort of the top, where the light's shining down. The sun's coming from the top. All right. Okay, so let's do a quick quiz. So I'm going to move to this next page, and let's do 2 examples. And I've written some poll questions. So let me draw a surface. This is try on your own. So I have a little parallelogram in 3D. So I know it's hard to draw in 3D, but really think it's sitting in coordinate space. And it's I've been coloring these things blue. So that's blue, and I'm going to have a unit normal coming down and out. So here is n. And let me draw this curve C. The C is the boundary, and I'm orienting C this way. So think okay, and then that's S. So I've got everything labeled now. My question is, does the orientation of S agree with C? And I'm going to upload a poll. So let me find that really quick. Polling. Okay. Parallelogram orientation. So why don't you see the poll I've just launched and see what you think? I'll write it down. Does orientation of C agree with orientation of S? And then we'll launch a second poll after this. And I'll draw my pictures. So I'm going to have a hemisphere here and a curve C right here. Okay, so we have how many people? We got 14 participants and 11 people. Okay, all right. So I'll end the poll, and the orientations do not agree. Okay, now let's see why. So we got 7 people guessing that orientations do not agree. So the answer is they don't agree. So the reason why is, if I drew little counterclockwise arrows at the base of the normal vector, as determined by by n. Okay, so it's going to be kind of, this is a tricky question that I designed, but they actually would look something like this. You got to realize they would look that way because you're kind of looking at the underside of the surface. So if I picked it up and flipped it, if I were in person right now, I'd be holding that surface and like flipping it around for you. The picture you would see is something like this, where the N is coming out of the page, and this, okay, I'll zoom in. Sorry. Okay. There we go. Okay. My counterclockwise would look like this, and my boundary would be going the other way if I looked at it from the other side. And those are not agreeing. So for that reason, the orientations don't agree. Okay, let's try again. I'll close this up, and I've drawn, okay, so, oh, Kelly asked a question. Using the left hand method, why does the previous surface example not agree? Okay. Okay, so let's do the OpenStax way. If I am, yeah, this can be fun. This is fun. Let's draw. So I'm going to zoom in for a second. I'm going to answer Kelly's question. So let's do it the other way. Let's think. Okay, it's so if I'm walking this way.
Wait, no, sorry, I meant the example from the previous.
Oh, okay. Which one?
Like the top, like either they're the same shapes, just two different methods, right? I don't see why, like for the left one, for example,
Yeah.
if you are the normal vector walking along the curve, then your left hand, isn't that not over the surface?
Okay, so this one for a second. Do you want to look at the picture?
Yeah.
Okay. So my little purple guy is walking the upright over the green, and the left arm, this is the heavy left arm, its shadow is sort of over the surface. So over there in that picture, maybe my picture's not great, but the left hand is hovering over S in that case.
But he's walking along the curve, right?
Yeah, that's
So
right.
he's facing us right now. So his left hand.
Oh, no. He's walking this way, so his eyes are here, and that's his vision. He's walking that way. Because he's walking determined in which direction determined by the green arrows.
Right. No, yeah, I agree. So if he's walking in that direction, like his hand is over the edge, isn't it?
Oh, did I say it wrong? I say the left hand should be hovering over the surface. So what did I say? The left hand should hover over S. The right hand is like not hovering over anything.
My confusion is that the left hand isn't hovering over the surface, right?
No, it is. It is. Like Kelly's correct. I think you got it backwards for this example. Did I? Here, let me try to think of a better way. Like the shadow. Do you see that the purple shadow is this thing that I'm drawing? Compare it to the bottom one. That is the same picture. Okay, let me see. Okay, so multiple people, which side of the curve is closer to us? It might be a perspective issue. So let me just draw the surface over here. So it's like you've got a plastic bag, sort of. This is like the plastic bag upside down. I think I see the issue. Okay, you're looking at the I see the issue. Okay, sorry everybody. The issue is that you're looking inside. So like this is open. This is open for us. This is confusing. I think this is the confusing piece.
All right, what do you mean it's open?
How do I say this? Okay, okay. Like take the X, Y plane. So here's X and Y. You're kind of looking at it from the underside. That my drawing was bad. This is the underside of like a hemisphere. So I'm looking up and in. So this is bad. I'm so sorry, everybody. Okay, like here's a better way to do this. Sorry. Okay, so think for a second. I'm drawing a purple sphere. the outside of the sphere is purple, and if you cut it open and looked at the inside, it would be red. Okay, so you're only seeing the outside. So what I'm doing right now is I'm now gonna cut it like with the Z plane. So the Z equals 0 plane, and now I'm looking at this shape. And so you still have this thing right here. Okay, it's all purple, and now what I've done is I've tilted it, so now you can see the underside, which has some red. That's what's going on. So I think people were thinking I was drawing the surface this way. I'm really drawing it this way, so you can kind of see the inside. Does that help people? Is that answered? Does that fix where some of the confusion was coming from? I realize now that my picture was kind of crappy. It makes more sense. Okay, okay. I'm sorry. Yeah, I realized that I wasn't communicating that very well. Hopefully that red kind of description helps. Okay. So let me draw this picture over here. So in this picture, I really want to explain what's happening. So this is a hemisphere, and I've cut it. So it's I cut it using the x equals 0 plane. So this is the outside that I've highlighted in purple. And this would be like that red internal part of the sphere if we were still doing the same color. So let's see, I was doing purple, so let's keep that. So we had a purple outside, but the inside of the sphere was red. Okay, so now let me give a normal vector, and I'm gonna give an orientation of the boundary. So I'm gonna orient the green curve this way. Okay, and let's see. Let's see. And how am I going to orient the n? So the n is, I'll do the outward normal vector. Do the outward one. Okay. So let's carefully think. Let's try to make sure that the picture makes sense to all of us before we think, and then we'll ask: does the orientation of C agree with orientation of S? Okay, so think about this, and then that's C, and I'll launch the poll. Hemisphere orientation. Okay, launch poll. All right, take a shot. Just tell me what you think. Yes, and Austin asked if the black lines are the black lines are the normals. Yeah, let me label that. That's N. Okay. And we're getting, okay. The black lines are the normals. The purple is the surface S. Yeah. Let's take about 5 more seconds, and then I'll end the poll. Okay, so these were the results, and we are getting the right answer. The majority is getting the right answer that the orientations do not agree. So let's do it the rotational arrow way. I'll draw. So okay, come on. So at this normal vector, we'll draw some counterclockwise arrows at the base. So I'm going to be drawing something on the purple surface. So this is on the purple surface. And we see that the little counterclockwise rotation about that N are fighting the green arrows near the curve C. So they do not agree. Do not agree. Yeah, I'm very sorry for my issue at the picture over here. Okay, so unless there are any more questions, let's move on. Because if you get the orientations wrong, you might get a sign wrong at times. So let's say some other things. So I want to note that a surface can have multiple what's it called? Multiple boundary components. So in the previous, all the previous examples, all the drawings that I've drawn today are, oh, I guess I can't, okay, I didn't share results. Okay, I'm learning how to do this polling stuff, okay. So in all the previous drawings that we've done, so look at this picture right here, it only has one connected boundary component. It's that square around the top. Here we've got one green curve, which is a circle, and over here in all these pictures there was, you know, only one green curve. But you know, you can have, let me draw a situation where you have multiple. So here we've sort of got an upside down tube of lipstick. Okay, so I'll use dashed to tell you that's behind the surface. So this is my surface S. It's got a boundary component up top. I'll draw that in green up here. And it's got a sort of a tilted boundary component down there. So I've got an outward normal like this, and that gives me an orientation of S. So I'm going to orient the top and bottom boundary components. So I'll put some arrows this way so we know how to orient the top, and the bottom I'll put some arrows down here. So this is going to be C1 and C2. Okay, so basically what I'll write is I'm going to write that the boundary of S is plus or minus C1 plus or minus C2. It might feel weird to be like, these are shapes, these are curves, and it might feel weird to like add them and subtract them, but you should note that there are certain mathematical contexts that make this notation actually precise. So it's actually okay to write a boundary is, like, you should read this as, you know, the boundary of S is, it might be positive or negative accumulations of C. So let's figure out, and the plus and minus is going to be determined by if we have agreeing, if the things agree. So let's see if we should be using plus C1 or minus C1. So let's come up here, and if I draw a normal vector close to C, and I do counterclockwise about that normal, I'm seeing that they're agreeing. So agreeing arrows tells us we should be using the plus. Okay, and then I'll do this up here in purple. Okay, so if I draw an arrow up here, and then I draw some counterclockwise rotations, I'm seeing that it's also agreeing with the arrows present on C2. So we've got agreeing arrows are going to tell us positive C2. So the final answer is going to be the boundary of S is a copy of C1 plus a copy of C2. And this is helpful because this is helpful for Stokes' theorem because of the following. I'm going to resize this. This would tell us that if we had some vector field, then the integral of curl v dot n over s dA, assuming I had some vector field v, I haven't even said anything, but if I had a vector field v, then I could actually write this as a positive copy of a single work integral about v1, about c1 v dot tds, excuse me, plus a positive copy over c2 v dot tds. Okay, this is if I had a vector field. If I had a vector field v, then I could set up this equation. Okay. So let me, okay. All right, let's do, all right, move pages. So let me know if you need me to go back. Oops. Okay. So let's do the following. Let's done some more examples. What makes n oriented here? Good. Okay, so Nicholas asks a good question. So the n is determining an orientation of S. you know, basically the n, you can think of n as picking a side to be positive. It's telling you how to move from the negative side to the positive side. I could have flipped it. I could have drawn an n that comes inwards, and that would have been a different normal, and that would have given me a different orientation, and everything would be flipped. That's a good question. If I flipped the orientation of n in this picture, then I would change the sign of that n that appears in that integral, making this entire thing negative, and that would be compensated for by the fact that the orientation of S would now disagree with both C1 and C2, and we would need to use minus and minus sign. So that's a really good question. Okay, but not in this case, because so n gives the orientation. That's right. And you can flip it. And actually, it's a fun game to see if you flip things, how does everything have to work out to be with the signs to make it all right? So let's do this. I have this sort of, okay, I realize I got to be really careful with the shapes that I draw. So I've got this sort of banana looking thing. Okay, it's a banana looking thing, and I sort of have cut the ends off the bananas. It's not really banana, but so here's my big surface, and I have an outward pointing vector n, sorry, and this is my S1, and I'll call this little cap my S2, and this is S3. So they're all three surfaces. So the full surface is going to be S. So you could write S equals S1 plus S2 plus S3. Okay. And I also have these two curves that you see. So I have C1. This is C1, and I have over here, this is going to be C2. All right. So, and the n that I have drawn on S1 is the same n everywhere. So it's the outward n. Okay. So let us try to figure out, again, what the boundary of S1 is. So let's look at S1. This is the big, okay, this is the big curve, the bigger middle chunk. Now the boundary of S1, it involves these edges, that one and that one. So I know it's going to be plus or minus C1, plus or minus C2. So let's figure out which way it's going to go. If I draw an arrow of a normal vector that's very close, and I draw a counterclockwise rotation, I'm disagreeing at C1, and so I have negative C1 right there. And let's do the same thing over here. If I draw arrows, I'm fighting. Okay, so again, that's minus, so I have the boundary of S1 is a negative copy of C1 minus a copy of C2. Okay, let's do the other chunks. So let's look at the boundary of S2. That's this cap up here. It has nothing to do with C2. C2 is on the far right side. So I just know it's either going to be a positive or a negative copy of C1. And you can actually just see right now that you can see that if I drew an arrow, it's getting kind of messy. If I drew counterclockwise rotation about the base, I'd be going along with C1, so it's positive. Okay. And then finally, boundary of S3 is going to also be positive C2. Okay. All right. So these, let me see. Okay. This is the information that we've gathered. I'm going to minimize it because we're not quite done with this. Size. Okay. And what was I have this. Okay, so I could say, you can start asking all sorts of fun questions. So I could say, what is the value of the double integral of curl of v dot n over S1 dA if all you know is the following two pieces of information? So if it is known that, okay, the single integral over C1 v dot t ds is, I'm just going to make something up, like 5. And the single integral over C2 of v dot t ds is equal to, let's say, -1. Okay. Well, we're going to use this fact, I'll highlight it right here, that the boundary of S1 is a negative copy of C1 and a negative copy of C2. And so Stokes' theorem says that this double integral over S1 of this curl, I haven't even told you V, by the way. V is just some vector field that is well defined everywhere. It's going to be -5 minus -1, which gives me -5 plus 1, which is -4. Okay, so there are all sorts of questions that you could ask. I could ask about the curl on S3 or the curl on S2, all sorts of different questions. Okay. All right. So think about some. Okay. We haven't actually done any like real calculus today. We haven't done any integrals or parametrization. So let's actually do a neat little example. So I'm going to say, here's a problem. It says compute the integral over c v dot t ds, and I have to tell you what all the data is, where v is the vector field -y comma x comma 0. So we've dealt with this vector field many times, and this is that it looks like a tornado, a positive a tornado that's twisting in a counterclockwise fashion around a vertical axis like this. Okay, so this is v. I shouldn't have done that vertical axis in red. That vertical axis is z. Okay, x and y. And what do I still need to tell you? I need to give you an oriented curve C. So I'm going to say C is the counterclockwise oriented. So counterclockwise oriented curve obtained by intersecting the vertical cylinder, that's x squared plus y squared equals 1, with a plane x plus y plus z equals 0. So let me draw the picture really quickly. Here's my cylinder, and I cut it with some plane, like I'll do it in green right here. Okay, so some plane cuts this thing, and my resulting curve is, I'll draw it in purple, something tilted like this. Okay, so that's my curve C, and it's going counterclockwise. All right. Well, now, like we've dealt with parametrizing these like curves of intersection before, and it can be kind of tricky. So, we could do all the work and find the parametrization and plug it into the equation. Sorry, set up the circulation integral and just do it, brute force it, or we can use Stokes' theorem. So you see that I got that purple curve drawn down there, but I also have another purple curve. I have one that's up here, which is the same orientation, but it's just a unit circle. Maybe, I don't know, let's say at height z equals 15, just high enough to stay away from that curve below. And what I can start to do is I can start to actually form a surface out of these two curves. I've got a red surface around here. I'm going to call that S. So the idea is that we could actually set up an equation involving 3 integrals. So basically what we'll do is we'll find a way of computing this number without actually ever having to parameterize the surface C, the curve C. So I will let C tilde up top be this oriented unit circle, and so we'll be able to see that the double integral of the curl of V dot n dA. Okay, I haven't told you what the n is. So n is the outward normal about my surface S. Is going to be, plus or minus the single work integral over C b dot t ds, plus or minus the single integral over C twiddle v dot t ds. And I see that up top we get negative, and at bottom we get positive. And so I just did the orientations really quickly. You can convince yourself that those are correct. So we see that the integral of C, which is the thing that the question is asking us for, is going to equal the double integral over S plus C twiddle v dot t ds. Okay, so this is what they're asking us for, and this is one way we can decompose the thing. And so I want to save some space. So I'm going to tell you why, in fact, the thing on the right is easier, or at least can be easier. So let me resize this. Okay. I think we've computed this before, that the actual curl of V is equal to 0, 0, 2. And if you remember, we had our warm-up question on Wednesday was, what is the flux integral where this was my vector field, and I'm flowing that, and I'm doing that flux over a vertical cylinder. And everybody got that question correct. Everybody said it would be 0, just because I know this is orthogonal to n. So that tells me that this piece right here is totally 0. So in fact, our equation becomes that the thing that they're asking us for is going to be equal to C twiddle b dot t ds, where this is the easier one. This is the flat circle of radius 1 centered up, I guess, at 0, 0, 15, and this right here is the wonky one. Okay, and I think you can compute pretty easily using r of t equals cosine of t sine of t 15 from 0 to 2 pi. I believe that this thing just becomes 2 pi. So that's the much easier integral to do than the one on the left. And look, we never even had to parameterize our crazy curve right there. Although you could, I know everybody in this class would be able to do that and would be able to get the 2 pi at the end of the day. But I mean, we could even make this worse. I can say, let r of t be equal to cosine of t sine of t, and then I'm going to do something like cosine of 15t. So this is some curve in the 3 space. It kind of looks like the edge of a 2-2. I mean, the bird's eye view is a circle going counterclockwise, but the height component is making me sort of oscillate like this. This is a horrible picture. But one could say, compute that work integral where this is C, and you're supposed to be doing a circulation integral over that wild curve. And you can just use that same argument. You can say, basically look at that picture right there. Oops, my thing's kind of slowing down. Okay. You can do this an argument where you can say that curve and the unit circle up top, I'll do that in purple, both bound this really strange looking cylinder that has a jagged bottom. And you could conclude that the value of the curve of the work integral over the bottom is equal to the value of the work integral up top, where the top one is much easier to do. So this is letting this is saving us. So Stokes saves us from having to do too much work. Okay, so I don't have enough time to go over an example another example, but there's one last thing that I want to say on this topic, and then we can be done for the day, is that I think it was either it was Monday or it was a full week ago where I told you the Stokes theorem for flat regions on the plane. I just want to take the time to show you that this is actually that what we learned a week ago for the flat stuff really can be interpreted in the Stokes theorem that we've learned yesterday. So Stokes for flat regions. This is, I remember that I said you might see this as Green's theorem versus 3D Stokes. My goal is that you can see that they're really the same thing. So in 3D versus in 2D, we had that the curl was a vector, and in 2D it's a number. Okay. For the 2D region, so our 2D region, I know that's kind of confusing, is a surface. So it's some wiggly wobbly 2D shape in 3D. But then in the, I'll say this is Green's theorem. And this is Wednesday. In Green's theorem, it was a solid region in the plane, and then the integral was a double integral of curl dot n dA over S, and this was the double integral of curl dA. No dotting, because it wasn't a vector over here. But the reason why you can interpret this right-hand column as stuff in the left-hand column is, to visualize it going from that way, from the left column to the right column, you understand the vector field, a 2D vector field, V of x, y is P comma Q. You can turn it into a 3D vector field by just saying V is P, Q, 0. Now you can check that the curl of this vector field is now going to be 0, 0, partial Q, partial X, minus partial P, partial Y. You can check all this stuff on your own. Okay, I've got 1 minute left. Let me just resize this. And so you can see that if you want to do the double integral, so you should think about a region, here is your region R in the plane in X, Y. If you want to look at this as a surface in 3D, it's just a flat surface in 3D with normal vector n. So this is now in X, Y, Z space, so that the double integral of curl V dot n dA is now equal to the double integral of 0, 0, partial Q, partial X, minus partial P, partial Y, dotted with 0, 0, 1 dA, and this just, you can see what happens. The last piece falls right off, and this is just the scalar curl. This is curl of V dA as a scalar. Okay, so I'm over time now, but I just wanted to show you that really this is it's the same thing that we've learned. This is just it's a more general thing of what we've learned a couple days ago. So I'm going to stop the recording and then you can ask me questions. Okay.